Welcome to this explainer. Today, we're going to explore a completely hidden dimension of our everyday lives. It's a super fascinating concept. The physical spaces we navigate daily, the ones that feel totally organic or, honestly, sometimes just randomly put together, are actually meticulously calculated machines. Every aisle, every single door, every workstation you pass is part of an invisible science designed with intense mathematical precision. Think of this explainer as our blueprint for the day. We're going to start with the invisible science of space, move right into strategy, flow, and waste, check out the Kanban signal, cover the principles of physical work, dive deep into the algorithms of layout, and then finish up with a never-ending blueprint.
Section 1. The Invisible Science of Space. Okay, let's dive right into this.
I want to ask you something. Have you considered the layout of the last grocery store or airport you visited? Really think about the bottlenecks. Think about the flow of foot traffic. Have you ever wondered why the milk is literally always in the back corner of the store? Or why your terminal connection requires a random tram ride? Well, from high-stress hospital emergency rooms to massive global transportation hubs, the way people and materials move is absolutely not an accident. If a hospital layout is flawed, it costs critical time. And in an ER, time is quite literally a matter of life and death. If an airport layout is flawed, thousands of passengers miss their connections, luggage gets lost, and millions of dollars just evaporate in delays. So yeah, every single footstep matters.
Behind all of this chaos are industrial engineers, specifically known as facilities planners. They are essentially the invisible architects of our modern world. Their whole job is to optimize layouts, handling systems, and networks to achieve very specific strategic objectives. But how do they actually pull that off? Well, they do it by predicting bottlenecks before a single brick is even laid. They analyze movement data, they evaluate the exact physical needs of a business, and they transform unpredictable human behavior into highly predictable mathematical models. They don't just see a building, right? They see a living, breathing machine with arteries and veins working tirelessly to make sure our environments operate as smoothly and efficiently as humanly and mathematically possible.
Section 2. Strategy, Flow, and Waste. Okay, at its core, effective workflow really comes down to three massive principles. Let's break them down simply because these are the absolute secret sauce to everything we're discussing today. First up is minimizing flow. In plain language, this just means figuring out how to move things as little as possible. If you don't actually have to move a box across the warehouse, just don't do it. Second is minimizing the costs of flow. This means making the moves you absolutely do have to make as cheap and efficient as you possibly can. And third is maximizing directed flow paths. This simply means making sure things move in a straight, logical line without constantly backtracking or crossing paths and causing giant traffic jams.
So, looking at the criteria for an optimal facility, we see things like planning for future storage, centralizing locations, minimizing receiving and put-away times, and making sure there's proper equipment spacing. But the one that really ties all those core principles together is smooth product flow. You see, by arranging a facility so that materials and people travel the shortest, most logical distance without backtracking, planners are actively maximizing those directed flow paths. They're basically smoothing out the bottlenecks before they even have a chance to form, which ensures that the journey from the loading dock directly to the customer's hands is as seamless as possible.
And that brings us to a brilliant little formula known as the work principle. The measure of work equals the amount of material flow multiplied by the distance moved. It's incredibly simple, but man, is it powerful. The ultimate goal for any planner is to minimize work whenever possible. So how do they do it? By minimizing flow. This means moving materials in practically large amounts. Think like moving an entire loaded pallet instead of carrying individual boxes back and forth all day. So you drastically reduce the total number of trips. Every single inch of distance saved is wasted energy eliminated. Section 3. The Kanban signal. Now that we understand the primary goal of minimizing flow, how do we practically execute that on a chaotic, super busy manufacturing floor? Planners use very specific strategies to hit this highly optimized state. Let's look at one of the most famous tools in their arsenal, the Kanban. It's a Japanese term that translates to visual board or sign. A Kanban is simply a signal, usually just a physical card, that tells a supplying workstation that a consuming workstation actually needs more parts. It's kind of like an internal customer order. The worker at Station B hands a card to the worker at Station A saying, "Hey, I'm ready for the next piece." Why is this so crucial? Because it directly tackles our second principle, minimizing the costs of flow. By only moving parts when a Kanban signals a direct need, a facility drastically reduces its work-in-process inventory. You aren't just blindly producing and storing huge piles of parts that nobody needs yet. It simplifies production control, clears up valuable floor space, and honestly, saves massive amounts of money.
Section 4. Principles of physical work. Okay, we've talked a lot about the macro flow of materials, but what about the actual people? Let's transition to the micro level of individual human workers. Because, let's be real, a perfectly mapped mathematical flow path is completely useless if it breaks the people who actually have to operate inside it.
So the crucial point here is the ergonomic principle. This is the science that seeks to adapt work or working conditions to suit the abilities of the worker. Facilities planners don't just crunch cold numbers all day. They have to anchor their abstract concepts to physical, human reality. Flow matrices and handling systems must ultimately align with real human capabilities and limitations. If a workflow is mathematically perfect on paper, but it requires a human worker to awkwardly bend over, say, 500 times an hour to pick up a part, yeah, that is a massive failure in design. Planners absolutely must optimize for the human body just as much as they optimize for the forklift.
Section 5. The algorithms of layout. Speaking of the math, let's transition into the mathematical heart of facilities planning. This is where high-level strategy literally becomes a physical blueprint. Now, what's really interesting here is how software jumps in to help us minimize the cost of flow. Planners use these complex algorithms like Craft and Multiple. These are what we call path-dependent layout heuristics. Now, in plain English, you feed the software data about how much your departments interact with one another, and it tests thousands of potential layouts by swapping departments around to find the cheapest, most efficient path possible. The main difference between them? Well, Craft might just test swapping two rooms that are right next to each other. But the Multiple algorithm? It casts a way wider net. It considers a larger set of two-way department exchanges across the entire floor plan at each step to hunt down that absolute optimal setup. It takes more computing power, for sure, but it finds hidden efficiencies that a simpler algorithm might just walk right past.
Let's see how this actually builds visually. This right here is an adjacency graph. Long before a single wall is built or a concrete foundation is poured, planners translate abstract relationships, like, how often the shipping department needs to physically hand things over to the packaging department, into mathematical nodes and edges. The thicker the line between the circles you see there, the heavier the relationship weight, meaning those two departments interact constantly. This graph is the raw data representation of maximizing directed flow paths. It shows exactly who needs to be next to whom to prevent unnecessary travel all the way across a warehouse.
And this brilliantly illustrates the final output. This is the block layout. It's the big aha moment where the mathematical algorithm from that previous adjacency graph becomes a tangible, physical floor plan. Those floating nodes and thick relational lines have been compressed, squared off, and shaped into actual rooms and departments. They fit together perfectly, like a giant jigsaw puzzle that represents absolute peak efficiency. The abstract math has literally drawn the walls for us.
To truly understand why all this complex algorithmic work matters, just look at the raw financial impact in the exchange data here. This shows the estimated savings, whether we're measuring in dollars, time, or distance, from simply exchanging the physical locations of two departments in a layout matrix. Notice how swapping Department 1 and 5 yields a massive savings score of 410. That's huge. Just by moving rooms around in a software simulation before construction even begins, facilities planners can drastically minimize the costs of flow, saving companies thousands, if not millions of dollars over the lifespan of a building.
Section 6. A never-ending blueprint.
As we wrap up this explainer, we need to look at the overall life cycle of a facility plant. You might think that once the building is built, the concrete is completely dry, and the machinery is installed, the planner's job is just done, right? Actually, scratch that. It couldn't be further from the truth. I absolutely love this quote from our source material. Facilities planning is never completed for an enterprise. Updating and continuously improving facilities is a must. Think about it. As companies grow, as consumer demands totally shift, and as completely new material handling technologies like, automated robots or super advanced conveyors are invented, the optimal flow changes. What was highly efficient 10 years ago might be a massive bottleneck today. To continue minimizing flow and maximizing efficiency, the layout has to constantly adapt. It's a completely dynamic, ongoing process of continuous improvement.
So I'm going to leave you with this one final thought. What invisible algorithms are you walking through today? The very next time you step into a massive distribution warehouse, a local hospital, or even just your neighborhood grocery store, try to look past the products on the shelves and the people in the aisles.
Look at the proximity of the departments, the flow of the shopping carts, the specific placement of the checkout lanes. You are walking through a living, breathing, mathematical equation designed to guide your every single step. Thank you so much for joining me on this explainer, and keep your eyes open to the hidden science all around you.